start yakking here. Yeah, so this is the third lecture, third and last lecture, and I'd like to actually talk about this is a very instructive thing to look at, the multiplication of free random variables. So it's of course venerable. Well, in the at the scale of time of free probability, it's venerable because it's like, I believe, the paper of Voiculescu introducing the S transform, which handles this multiplication, is 1987. Yes, so of course, but still, I think that it's very instructive to kind of look at it from various angles. And I must tell you from the beginning, I have a one important equation. Oops, what's going on here? Yeah, so it moved. Okay, I have one important formula which will appear again and again. So it will be called important formula. Okay, and it's gonna keep appearing. So that's actually my goal for the talk, is to sell that formula repeatedly. Okay. So anyway, so let me start with the review. So not yesterday, 2 days ago. Yes, it was a discussion about these semi-multiplicative functions, and they form a group which was called G-Twiddle. Yeah. Okay. So let's review that. Yes. The Ping is very nice and is posting these files. So if I'm not going to review fully the notation, but it is available if you want to see it and go to the website of the conference. So anyway, so yeah, so we look at the collection of pretty much pairs pi sigma, which are non-crossing partitions of 1 to 3, and pi is less or equal sigma in the reverse refinement order. Yeah. And we think of them like pi sigma really encode an interval in the lattice of non-crossing partitions of 1 to 3. Okay, and we take so the system of all such pi sigmas is denoted as p non-crossing superscript 2. Okay, and we look at the function. So we have a big group of functions defined here. Yes. On this set of pi sigmas, where actually, like, in order to get a group, we impose that f of pi is always equal to 1. Okay, and then you convolve these functions as if it was a matrix multiplication, and in fact, this is something that this is actually a repeat of the Tuesday lecture. Yes, where I even said that actually, yes, this you can view these functions as upper triangular matrices. This is with ones on the diagonal, which is why they form a group. Okay. Yes. Okay. And now let me go again at G-Twiddle. So F is a group, and G-Twiddle will be a certain subgroup of F. And let me now remind with a bit more detail than on Tuesday how that is found. Yes. So as I was saying, so for every pi less or equal sigma in a non-crossing partitions lattice, you consider this interval. So all the rows sitting between pi and sigma in the reverse refinement order. And then there was a factorization lemma which appeared in the lecture from Monday, and I'm repeating here in a bit more kind of, it's a like still very easy, but a bit more general than what I said on Monday. Namely, look what you do. So let sigma, the bigger partition, let it be written explicitly as W1 to WK. So it's got K blocks. And then for each of the blocks WI, you see how it is broken into pieces by pi, right? Because pi is smaller. So pi is obtained out of sigma by taking the blocks of sigma and breaking them into pieces in a non-crossing way. Each of the WIs gets to be broken in a non-crossing way, so that you get pi. Yeah. And you take each of these WIs and you look at how pi divides WI into pieces. Yeah, and this is a non-crossing partition of a number of points, which is WI. Is that business with restrict and relabel, which I was talking about on Monday. Yeah, so you get pretty much K non-crossing partitions of sizes, cardinality of W1 ... up to the cardinality of WK. Okay, and it's easy to see that actually. So this is what I advertise on Tuesday as the isomorphism iso to top. Yes, because pi sigma is broken as a Cartesian product of k things. Yes, and each of the k things is an interval starting from this restricted relabel partition up to the biggest element. So one sub something is the partition with one block. And the definition on Tuesday, repeated here with, as I'm saying, with a bit more detail, is that so you say that G is semi-multiplicative when it follows this factorization. So G of pi sigma must be the product of these fellows here. Yeah. And it's called semi because actually the multiplicativity was done, as I showed on Tuesday, in 2 steps, and this is step 1. This is step 1, and for the moment we ignore step 2. So that's just semi-multiplicative. Yeah. Okay. And this is the group G twiddle. It can be verified that this is indeed the group. Yeah. It is a subgroup of F. Okay. From the definition, I think I can scroll a bit this way. Yeah. So you see, this formula makes clear that you know G completely if you know the values from things to the top. Yeah. So if you know these values, you know all the G of pi sigmas. It's not hard to check that vice versa. Yeah. You can actually, so somebody gives you a family of numbers Z of pi. Okay. You can then define a semi-multiplicative function by prescribing G pi 1n to be those Z of pi's which are given. So you are free to choose them. The only thing that you have to be careful with is that these Z's given by the other person have to be Z of 1n must be 1 because G of 1n must be always 1. Yes, by the definition of the group F. Okay, so this is G twiddle. Yeah. Okay. And this is what we wanted to remember about it. Yeah. Okay. Good. Now I'd like to look at G. Yeah. So G is the smaller group where we also take into account the second step of that canonical factorization that I talked about on Tuesday. Yeah. Okay. So in order to explain how G works, so in order to explain the second step, it is essential to look at this Creveras complementation map. This was reviewed, for instance, by the talk of Jorge on Monday. But anyway, let me go at it again. Yeah. So you see, like you do the following game. So somebody gives you 2 non-crossing partitions of endpoints, pi and rho. Okay. And then you can do the following thing. You can take the pi and you can place it on the first odd positive integers, 1, 3, 5, up to 2n minus 1. And you can take rho and you can place it on the first n even integers, 2, 4, 6, So together, this gives you a partition of 1 up to 2n. Yes. But of course, this may or may not be non-crossing. Yes. Because for instance, in this example, so pi becomes this partition which groups 1, 5, and then 3 is a singleton. Rho is 2 in a singleton and 4 and 6 together. And even though pi and rho separately were non-crossing, but the aggregate is crossing. Yes, has a crossing. Okay. And the fact is that if you fix the pi and if you look at the rows which in this game produce a non-crossing thing of 2 endpoints, there is one of those rows which is bigger than all the others in the order, and that is by definition the Creveras complement. Yeah. So for instance, for this pi here, what can I do? So I need actually like to fix my thing. What I have to do. So imagine that pi is done in red, and I need to do a row in blue as big as possible. I can connect 2 to 4, and then 6 must stay in a singleton. So when I divide by 2, this is the Creveras complement for the given pi. Yeah. So this was the review of Creveras complementation map. And before saying what is G, let me also mention on this slide some easy properties which you see for this map. So it is an order reversing bijection. Yes. So bigger is pi, smaller is its Creveras complement. In particular, the minimal element of the lattice goes. So this is 0n was the partition into n singletons. the Creveras is the partition with one block, and vice versa. Yeah, so it is an order reversing bijection. It swaps these two elements, but in general, if you apply it twice, you don't get exactly pi. What you get, you get a cyclic rotation of the labels of pi. So still there is some good symmetry here, namely that if you apply pi twice, you get a partition which is not exactly pi, but you are sure it has the same block sizes as pi, because you are just cyclically permuting the labels. Okay, and I can take this definition, which is a bit different from what I said on Tuesday, but it's equivalent. So in this group G twiddle of semi-multiplicatives, let's look at those which respect pi. Which respect the Creveras complement. So you want, if you take the interval from pi to 1n and you turn it around with the Creveras complement, so pi goes to its Creveras complement, 1 goes to 0, yes, and they go in reverse order. So just put this requirement. You want G to satisfy, so in addition to the multiplicativities to the top, which are part of the semi-multiplicative thing in G twiddle, also throw this one in. Yeah, okay. And the G's which satisfy this, we call the multiplicative, and this is the group G. Okay, and okay, so now same as with G twiddle, let's retain some points about this smaller group. So this is, it can be checked, it is a subgroup of G twiddle. Okay, and now the thing is, actually it is much smaller, because the condition which I put, which was, yes, I can scroll a bit and have it here. Yeah, so I was just asking this innocuous condition, but this actually forces the function G to be completely determined by values at full lattices. So 0n, 1n, this is the interval from from bottom to top. This is the full lattice of non-crossing partitions of 1 to 3n. Yeah. Okay. And why is G completely determined by that? Because well, first of all, it is semi-multiplicative, so it is we knew already that it is determined by the values G of pi to 1n for various pi's. But now further, this one you write it as I said, from G of 0 from Creveras of pi, and here there is semi-multiplicativity which factors, because this interval factors as a product of things to the top, which actually are full lattices. Yeah. And the semi-multiplicativity then gives you this factority. So then this means, yes, pretty much that actually a function in G is determined by a sequence of numbers. It is a lot more particular than what we had in G twiddle. Yeah. So a sequence of numbers is giving a function in G. This is repeated here, yes. So it is completely determined by its values like this. And again, there is a converse, like you got some freedom here. Like somebody gives you any sequence. Of course, the concern is with the beginning. So alpha 1 must be 1, but otherwise any alpha n's, then you can prescribe a G in this group of multiplicative functions G, which has G of 0 and 1n equal to the given alpha n's. Yes, and how do you get it? Well, then you extend to G pi comma 1n by putting exactly so this is the formula from the preceding slide. I think I can probably recover it. See, it's here at the top. Yeah, okay. So this formula at the top, where now these things have become alphas, alpha sub wj. Yeah, so alpha sub cardinality of wj. You see it here. Yeah, so you have like pretty much these functions. They are determined by sequences of complex numbers, and where alpha 1 is 1 due to my kind of I like to be in a framework where I have a group. So that's the alpha 1 equals 1. Okay, and there is this important formula which is about to come up. So it's going to come up like 4 times. So important one is coming when you check the convolution of 2 functions from G. Yeah, okay. Let me say right away, because it's not going to be room on the next slide, that actually when you see this formula, important one, and you consider that symmetry of the Creveras map, that it preserves the sizes of blocks because it is a cyclic rotation of the labels, you get this relevant fact that this group is commutative, unlike G twiddle, which is much bigger and not commutative, but this one is commutative. Okay, so now let's look at the convolution. Two functions in G, let's convolve them. Okay, and how do we convolve them? Well, we take these sequences of numbers which we know that they determine, so G and H are my two functions, so alpha n's determine G, beta n's determine H. Okay, and then their convolution will be determined, well, we will be determined by a sequence of gamma n's. Okay, and how do you write gamma n in terms of the alphas and the betas? That's the game. Yeah. Okay. And you start working on it. Gamma n, yes, is G star H at 0 and 1 n. Now, what was the definition of the convolution in general in the biggest framework F that we started with? It was summation all the pi's from 0 to 1, but this is everything in the lattice of non-crossing partitions here. G 0 n to pi, H pi to 1 n. Okay, now H is multiplicative, so we turn it around and it is G from 0 to pi, H from 0 to Creveras of pi. Okay, semi-multiplicativity, as I wrote already a bit earlier, factors this thing. G0 pi is a product of alphas, H of 0 Creveras of pi is a product of betas. Okay, replace everything, and this is the important formula, first incarnation. That when you do the convolution of two multiplicative functions and you want to write the gamma in terms of alphas and betas, this is what you get. And what do you get? Okay, so let's recap. Let's say the words. Yes, so take a p non-crossing, pi non-crossing. Okay, and you do like this. You do a product of alphas indexed by the sizes of the blocks of pi. Then you do a product of betas, which is indexed by the sizes of the blocks of the Creveras complement. So you pair pi with its Creveras complement, alphas and betas, multiply everything together, and then you sum after all the possible pictures of pi's. Yeah, that's what you do. That's the important formula, and we have it now. This is first occurrence. It appears as explicit description of the convolution of multiplicative functions. Good. So now I'm done. I'm done with the first two sections of my lecture, yes, because I have also reviewed G. Okay, and now let's discuss why G encodes the formula for the multiplication of free random variables. Yeah. Okay. So therefore, now we have to go to a non-commutative probability space, which I do here. Yeah. Okay. And as I had on Monday, yeah, this is the notation for the family of multilinear functionals which are giving the free cumulants of this space. Okay, and now I take, okay, I assume, yeah, that after almost 4 days of conference, yes, everybody knows. Anyway, so assume I never said in my course what it means that A is free from B, but I'll go ahead with that because I hope this is right. Yeah, and look what we do. So take two free elements. Okay, introduce some alphas and some betas. Okay, namely for alphas I take the moments of A, so phi of A to the n is alpha n. Yeah. For betas, I take the free cumulants of B. So beta n is kn. So this is a n linear functional. Put their n arguments all equal to B. Okay, and bang! Look here. So important formula for the product AB. The moments phi of AB to the n are expressed in terms of the alphas and the betas. And here you recognize that's exactly the right-hand side is identical to what we had in important one. So important one and important two, they have identical right-hand sides with, of course there is a difference on in what's the meaning of the alphas and the betas. But again, you take the alphas, which are moments of A, multiply them together according to what the blocks of pi tell you. Okay. Take the betas, which are the free cumulants of B, multiply them together according to what the Creveras complement tells you, multiply together sum over pi. Yeah. Okay. Now I think it is relevant, yes, to say yes, because yeah, that's the charm of this important formula. Like why does it appear in these different ways? And yeah, this is the fundamental result of free cumulants. Again, something that I kind of glossed over. I'm throwing it in now. which says actually in a more compelling way, it's an if and only if statement describing free independence in terms of free cumulants. But what we take from there here is that any cumulant, free cumulant, where you put entries which contain both some A's and some B's, will have to be 0. Yes, it's going to be a mixed free cumulant, and mixed free cumulants are 0. Yeah, okay. And there is a converse to that, as I'm saying. I'm not elaborating on that line. But the fact is that, okay, so I'm saying, what's the proof of the important equation 2? Okay, take phi of AB to the n, write AB to the n as a monomial, as a product of lengths 2n in A's and B's. So alternating A's and B's. Evaluate this with the moment cumulant formula for non-crossing with non-crossing partitions for free cumulants. So you get a summation, since this is length 2n, you get a summation over non-crossing partitions of 2n points. Okay, and here it's a product. So for every theta, say such non-crossing partitions, you take all the blocks of theta, you restrict your 2n tuple AB to that block, and take the corresponding free cumulant. Yes, but if you make the mistake to have a block U which picks both A's and B's, it's gone. Yeah. So you must only take U's. You must only allow blocks U which either only take A's or only take B's, because you don't want mixed cumulants. Okay. So this means that every U has to be contained either here or there, either in the odd numbers or in the even numbers. Yes, but then exactly this is like when I reviewed Krevera's complementation, I said this is exactly the situation when theta is of the form pi odd union with a rho even, where pi and rho are two partitions of n points each. Yes, pi is placed to get the theta on 1, 3, ... up to 2n minus 1, and rho is placed to get theta on the other side. Yeah. Okay. And then the fact that theta is non-crossing amounts precisely to the condition that rho is less or equal Krevera's of pi. Yeah. Okay. And then here my slide is running out, so I'm just gonna say, okay, so this here you continue. If anybody cares about that, it's very easy. Like just take a pencil, and then what happens? This sum over theta becomes a double sum over pi and rho. So leave the summation over pi outside, do the summation over rho inside. You're gonna get exactly some Krevera's of pi appearing. Okay. So anyway, so this is arguing, yeah, like this is really happening. Yes. So free independence really gives you this same important formula here. Yes, in these guys. Okay. Okay. So now then combine important 1 and important 2. They had the same right hand side. So then what I'll do is okay. So look what I do. I do the following gimmick. So if I take an element in my non-commutative probability space which has phi of a equals 1. Yeah. Okay, I create some multiplicative functions. Let me call them U sub a and R sub a. Yeah, okay. And these were, remember, like the functions in G, they are determined by prescribing them on interval 0 and 1n. And you can do that whichever way you like. Okay, so we like to do it. U sub a is with moments, R sub a is with free cumulants. Yeah, okay. Okay, and then if you go back to important 1, yes, and compare it to important 2, and use the fact that they had the same right hand side, but important 1 had some convolution, important 2 had some moments. Okay, then this is you get a very nice concise rephrasing of important 2. So let's call it, this is the important formula to prime, which says that U of the product where A and B are free. Yes, A is free from B. Then their product has the moment thing, the moment function is a convolution, something from A, something from B, namely moments and cumulants. Okay. Now here we do a little other, put another sticker on this to make it like kind of it's U and R, but we can make it be only with R. Yeah, and why that? Because actually U and R, so U and R, okay, here there, yes. So U was moment, R was free cumulants. There is a moment cumulant formula which connects them, okay, which is written here, okay. So U in terms of some other R's, okay, but this is exactly, you can recognize as a convolution in the group G. Yes, so it's just a sum, because here you put some ones as convolution, as the partner to create the convolution from pi to 1n. Yeah, okay. So actually the UA and RA, they are related by convolution in the group G with a universal object. Okay. So then the equation which I had before, which is written here in this proof at the bottom of the slide. So UAB equals UA star RB. Okay, but the UAB is replaced as RAB star this G. So this silly notation is because this appeared in lecture 2. It was the transition function from free cumulants to moments. It was one of several transition functions which appear there, but somehow I'm maintaining the notation. So okay. So but anyway, so UAB is written as RAB star this function. UA is written as RA star this function, and looked it would seem that there is a bit of trouble, but there isn't, because this is a commutative group. So we can move GFCM to the right here on the right hand side, and then multiply with its inverse, and we get precisely this formula. Yeah, and this formula, then what does it say? That's kind of the conclusion of this part of the lecture. It says that the convolution in the group G, this group of multiplicative functions G, if you kind of think of it in the right way with this encoding by functions RA, this is capturing the algebra of multiplication of free elements. Yeah. Okay. So if you encode the elements with their free cumulants, then the multiplication of free elements is captured by the multiplication operation of this group G. Wonderful. Good. So I've done this too. Okay. So now I'll throw in another occurrence of the important formula. Yeah, and here now we are kind of going towards like we want to look at Hopf algebras, and specifically at the Hopf algebra of symmetric functions, which is one of the nicest possible Hopf algebras that you may want to consider. Yeah, so SIM. Okay, and so let's review SIM. Yeah, so algebra of symmetric polynomials in a countable family of commuting indeterminates Ti. Okay, but actually I'm not going to think about the TIs much, because actually there is a fundamental theorem of symmetric functions which says that actually this is the polynomial algebra in elementary symmetric functions. Yeah, okay. So the elementary symmetric functions, it's kind of formal sum of the TIs, formal sum Ti Tj with I smaller than j, etc. Yeah, okay. And any symmetric function is written in a unique way as a polynomial in these elementary symmetric functions. So pretty much actually I can think of SIM as the algebra of polynomials, commutative polynomials in a countable collection of indeterminates which happen to be denoted E1, E2, ... En, etc. Okay, good. X of SIM is the set of characters by which I mean, so this is an algebra. It is an algebra of polynomials, really, as I just pointed out. Yeah, okay. The functions which are linear, multiplicative, and send one to one. Okay, and because it's an algebra of polynomials, actually giving a character of SIM actually comes to giving a sequence of numbers again. Because if you give the chi of ENs, then you have determined your character, and any free choice of chi of ENs is allowed. Yeah. Okay. So this is X of SIM, SIM and X of SIM. Okay. And the fact is, we don't want. The trick is that we don't want to work with the elementary functions or the power symmetric functions or some other kind of well-known symmetric functions. We want to work with some less known symmetric functions. Actually, where I work with that on this with Mitya Masnak, and who's an expert in Hopf algebras. And at the time when we were working on that, he didn't know how to name them, but later on turned out that they are called parking functions, symmetric functions. I call them Yn. Yeah. Okay. And how do I put? Okay, so y1 is 1. Actually, every yn is homogeneous of degree n-1. So y1 in particular is homogeneous of degree 0, so it is 1. Okay, and then let's look a bit further. So y2 is e1, y3 is e2 plus e1 square, y4 equals e3 plus 3 e1 e2 plus e1 cube. And what do you see? For instance, y3, you see a summation over non-crossing partitions of 2 points. Yeah, so E2 corresponds to the partition of 2 points which keeps the points together, and E1 square corresponds to the partition of 2 points which separates the points. Yeah, here there are 5 terms which correspond to the 5 partitions of 3 points, all the points together, all the points separated for E1 cube, and 3 ways of separating 1 point from the other 2. And in general, Yn, you do a summation, so you take all the non-crossing partitions of n-1 points, and you do a product here, E pi, which is defined here, is what you have for E1, E2, or E1 cube, or and so on. Yeah? So there's a nice formula which writes these y's in terms of elementary symmetric functions by using summations over non-crossing partitions. One thing to observe is that if you want to start the y's with y2, yes, you see that actually, so always every yn starts with a term which is e sub n-1. So y2 is e1, y3 is e2 plus some lower order stuff, y4 is e3 plus some lower order stuff. So it means that actually you can write vice versa the e's in terms of the y's, and from here it's easy to see that actually you can also view, if you so like, and I like to do that, the algebra of symmetric functions, you can view it as polynomials in the y's rather than the e's. Yeah, and this has the perk that actually, if I want to define characters of sim, instead of saying that I prescribe them on the e's, I'll say that I prescribe them on the y's. So I prescribe the values chi of yn, and starting with n at 2, and this will give me a character of sim. Yes, so I can control the characters of sim in terms of these other symmetric functions. Okay, good. Okay, so now comes the trick that actually sim is more than just an algebra. There is a nice co-multiplication on it. Okay, and the co-unit and the grading, which I didn't mention. So it is actually what people call a graded connected Hopf, well, by algebra, which is automatically a Hopf algebra. So very kind of an orgy of terms here. But anyway, so there is a let's look at this one. So there is a two algebra homomorphisms from sim into tensor product with itself. That's the co-multiplication and the co-unit going into the scalars. Okay, and because as I was saying, so any unital algebra homomorphism on sim, I can prescribe it. I can prescribe it by assigning it on the ENs. Yeah. Okay. So epsilon sends all the ENs to 0, but more importantly here it's the co-multiplication of the elementary symmetric functions. Yeah. Okay. Okay, and what's the business with this? Like, if you have this and you have like the co-multiplication has to be co-associative and all sorts of things, yeah, then you get a structure of algebra on the characters. So X of sim becomes a group. X of sim becomes a group, and what's the group operation on this group? So take two characters and convolve them. What do you do? So you take the tensor product of the two characters and apply them to the sum of tensors which comes from the co-multiplication. So pretty much you do delta of En, which is written above, yeah, and then you apply for every term here, you apply chi1 on the first component and chi2 on the second component. So you get this. Yes, this is how the convolution works. Yeah. Okay. So X of sim is a group. Okay. Now the point is that I don't want to look at X of sim. I mean, this is the group that I look at, but the way I want to describe it is in terms of my Y's. Okay. And so turns out that, okay, so if you write, actually this is not an easy, not like requires kind of some head scratching. Yes. So to do the but theoretically, right, I mean, this is clearly determined, like the Y's are written in terms of the E's. You know the delta of the E's, therefore you can write delta of Yn in terms of elementary symmetric functions, and then you can convert back to your Y's, and miraculously you get this very nice formula, which already has the flavor of being important, right? Because you see, you get a product of Y's indexed by the blocks of pi, and the product of Y is indexed by the block of the Creveras complement of pi, only that they're in a tensor product now. The tensor disappears when you move to convolution of characters. Yeah. So as a corollary of that formula, you get this. So if you want to convolve to characters, the way to introduce some alphas and some betas. So you do the first character on the Yns, called these alpha n's, and the second character on the Yns, called them beta n's. Okay, and then when you do chi1 star chi2 of Yn, what do you do? So you do chi1 tensor chi2 on this delta. So means that you apply chi1 on the first component here times chi2 on the second component. Chi1 and chi2 are both of them multiplicative, so you get the product of alphas times the product of betas. So again, the right hand side is the same thing with alphas and betas multiplied sum over all the pi's. Yeah. Okay. And then what do we get from here? We get that actually, so because the important formula gave us the convolution on the group G, and also with this smart way of using the Yns gives us the convolution in X of sim. So pretty much we get that X of sim and G are isomorphic, and actually we can write explicitly how the isomorphism goes. So for every character, take the multiplicative function, which records. So the values of chi at the Yns are recorded. Remember, like for a multiplicative function, this kind of sequence G at 0 n 1 n is what determines the function. Yeah? Okay. So that's then the conclusion of this part in the end. So we have this group G, yeah, and this group G turned out to capture the algebraic formalism for how you multiply free random variables. But now actually G is the group of characters of sim. So essentially you can say that that the group of characters of sim is telling you in a certain way how to multiply free random variables. Yeah. Okay. Okay, and I want to I want to mention like two things, like how this discussion can be continued. Like it will not be continued today, but I can mention these directions. In fact, one of them will be continued today because there's the talk by Daniel coming after mine. So, anyway, so one thing is. Like this is a well-known kind of thing that you can do in a connected algebra, such as sim, that you can take log of a character and you get you arrive into a space of so-called infinitesimal characters. Okay, and then you can take the log of the character which corresponds to some to some multiplicative function, but that multiplicative function can in turn correspond to an element A in a non-commutative probability space, and playing with that, you can retrieve you can somehow rediscover the S transform of Voiculescu, yes, which I was saying was the first and perhaps the nicest way of handling multiplication of free random variables. And for that, for this procedure, so there is a section devoted to that in this paper with Masnak. It's now fairly old, where we show how indeed you go. So there is something which you can do in several variables to some extent, but that I don't think was so successful. But in one variable, which is what I showed you today, you can rediscover the DS transform. Okay. Another idea, more recent, yeah, is this. So G was a subgroup of G Twiddle. Okay, and turns out that somehow in the same spirit as what I showed, it is possible to connect to construct a graded connected by algebra, which in the paper that I'm referring to is called T. Yeah. Such that G Twiddle is identified naturally as group of characters of T, and moreover, so G is contained in G Twiddle. This corresponds to the fact that T surjects naturally as Hopf algebras onto SIM. Okay, so T has a homomorphism onto SIM, which dualizes to a map between character groups going in the other direction. And when you identify X of SIM to G and X of T to G Twiddle, that's exactly the inclusion. Yeah, and I believe Daniel will explain how this goes in his talk. And this is following the paper that I also mentioned several times in the lecture on Tuesday. Yes, with Celestino, Ebrahimi Fard, myself, Perales, and Witzman. Okay. Yeah, so good. So all the good things come in series, and I had already the important formula coming 3 times. But anyway, so I have here a little thing at the end to point out that actually, like a force occurrence. Yeah. First of all, let me mention this amusing, well, amusing. I think it is more than amusing. It is an interesting and promising thing that you can study free independence by using Boolean cumulants. Here the Boolean cumulants. When I say beta, I mean kappa superscript Boolean. So somehow this sneaked from some older writing. So these betas, these are actually kappa superscript Boolean, the Boolean cumulants of A phi. And there is actually, it is definitely not as good as in the result of Speicher about vanishing of free cumulants, but you can say exactly how a Boolean cumulant, which has both has entries from 2 free algebras, how do you write it as a sum of products where you separate the variables from the 2 algebras? Yes, so say there are some variables, red variables from a subalgebra A1 and blue variables from a subalgebra A2, where A1 is free from A2, and then you have a mixed Boolean cumulant with red and blue. Yeah, and then you know how to write it as a product of red stuff times the product of blue stuff. Okay, and it's again it's an interesting thing because you use non-crossing partitions, even though it's Boolean cumulants, which seem to live in a different world. But actually, the conditions which are satisfied by these partitions. So you see that there are only 2 terms. And the conditions which you look is this, like separate red from blue. That's one condition. Connect, so be irreducible, connect 1 with 6. Yeah, so you see like this is, so see like this term, yes, it says A1, A5, A6. This is one block. And A3 in a singleton. This is the other block, and then in blue it is A2, A4. Yeah, and then this is the other term, and then actually so being separate red from blue and connect 1 with 6 still would allow these ones, and these ones are ruled out by a property which we call vertical no repeat, because actually so for instance this one here, you see this block 3 is seeing the block 1, 5, 6. So you could just edit here, yeah, and you could make a bigger block, and this is not allowed. Yeah, so if you look like in a non-crossing partition, every block which is inner has a parent block, which is the one that it is immediately nested inside. So 3 is nested inside 1, 5, 6 of the same color, not good. Here 5 is nested inside 1, 1, 6, same color, not good. Yeah, okay. And you can actually play that, and you can, it's interesting to study like this basic free harmonic analysis, sum of two free elements, product of two free elements, commutator, anti-commutator of two free elements, which were always, since forever, kind of studied with free cumulants. You can actually take a stab at them with Boolean cumulants and see what happens. And again, like this is the paper, which does to some extent that, and does some examples of free anti-commutators treated with Boolean cumulants. But let me point out, since it was all about this important formula, that actually, if you focus, okay, so here they are back to case, because so these are the T-Boolean cumulants. Yeah, so if you want to describe the multiplication of two free elements in terms of Boolean cumulants, surprisingly, it's exactly the same formula, this important formula that you had for free cumulants as well. So case T equals 1 gives you here free cumulants, and this is the formula which we had earlier in the lecture. Yes, it was the important -2. Yes, it was the case T equals 1 of this formula. If you make T equals 0, it's how to describe the multiplication of two free elements by using Boolean cumulants. It's exactly the same, and in fact, it's exactly the same for every T. Yeah. So yeah, this is proved in the paper with Celestino, Ebrahimi, Fard, Perales, and Witzman. Yeah. By using considerations on the group, like the certain important elements from the group G Tweedle turn out to belong to the centralizer of the group G, and somehow so we do a nice argument there, which is group theoretic. But anyway, so probably direct combinatorial proofs surely must be possible, because remember, these T-Boolean cumulants were done with by taking T to the number of inner blocks of a partition. So it's lots of discussion with pictures with inner and outer blocks. But anyway, so I find this to be quite intriguing and somehow promising, that you can use different types of cumulants to get at the study of free random variable. And that's it. Yeah, that was my thing for the day. Yeah. Thank you.
Thank you. Any questions in the audience? Yeah.
So maybe you already mentioned this, but what's the antipode in the above algebra of symmetric functions, and is that like relevant in G?
For this, no, I think it would be relevant if you start looking at. So I think I can't remember. Like surely there are very precise formulas, but I don't remember what it does to the EIs. I believe, for instance, if you take the power symmetric function, which is what's called a primitive element, those are sent to their negative by the antipode. So then you can work your way from there, from the power symmetric functions to elementary symmetric functions or other systems. I'm sure, like I don't know that from the top of my head, but I suspect this is something which is probably textbook material.
Any questions? I have a question actually. Do we have like something infinitesimal T-Boolean cumulants, and can we get afterwards like some similar formulas when we have product of infinitesimally free elements?
Oh yeah, like definitely there are the infinitesimal Boolean, and I think Daniel can answer that better. And also Peilun can answer that.
No,
better.
the T-Boolean, I mean, infinitesimal T-Boolean.
The T-Boolean. Yeah, T-Boolean. The T-Boolean, I don't know. Yeah, so yeah. Didn't try. I don't know. So this is like my lectures were all in the realm of the situation where you take one functional a phi. Yes, and indeed there is another order of business when you take a, phi, and psi. There are several ways look at cumulants in that framework, like at least, I don't know, three ways. Like there are these infinitesimal ones, also the second order, also the C3 of Bose-Coe. So I don't know, actually maybe then Daniel can say right away. So did you people do infinitesimal for the T-Boolean?
No. No, we
Did
haven't
you
done
say
that.
yes or no?
Okay. Any other questions here or on Zoom? Okay, if not, then let's thank Endo again.